Hi class, this is the lab recording, I should say, that reviews the PhysioEX activities that go with Lab 8. So in these activities that we're going to go through 4 of them. We're looking at different variables and how they affect blood flow. All right, so we're first going to look at the effect of the radius of the blood vessel on the blood flow. So we're going to keep constant in these experiments the pressure at 100 millimeters of mercury, the viscosity, so the thickness of the blood, and also the length of the vessel, the fake vessel we're looking at. So those are held constant. Our setup is that we have basically 2 tanks, a dispensing tank of blood. Here's our blood vessel, and then a receiving tank. And of course, we can manipulate different variables in this. So what we're going to do is it says to increase the flow tube radius to 1.5 millimeters. So I'm going to do that. And then it's going to, let's see, we've got a question. So what is the driving force for blood flow? So we've got viscosity, we've got a pressure gradient, we've got resistance, we've got laminar flow. Well, it's a gradient. Okay, submit question. Let's see. All right, so now we get to start the experiment. And we have to be patient. It's actually going to move really slow. We're at 1.5 millimeters of the radius of the blood vessel. And you can see it's going over. All right, it's over there. We're going to hit record data. We've got it. So our flow rate was 4.0 mils per minute. Now we get to refill it. And unfortunately, it's going to take the same amount of time to refill. It's going to take just a bit. All right, almost done here. We need to get all of it back. Okay. We've got a question. What do you think will happen to the flow rate if the radius is increased? So if we're increasing the radius, this is actually a weird wording. It says the radius is increased by 0.5. So going from 1.5 to 2. So we're increasing the diameter of the blood flow. So we would actually, holding everything else constant, we've increased the area that the same amount of blood can flow into. So the flow rate should really slow down. Okay, let's see, where do I go next? Here we go. So now we're going to go to 2 and we're going to hit start and see if there's a change in the flow rate. And there is. Good, because we have to pump it back over too. To be honest, I had a little bit of trouble with the wording there on the increase of the radius. And when I did this to preview the experiment, I actually answered the question wrong. And the explanation that PhysioEX gave me just didn't make sense because of the way the wording is. But usually if we decrease a radius, that's applying resistance, which makes the blood move faster. All right, so we are now going to start. Oh wait, I've got to refill. Sorry, I'm getting distracted. So we went to 12.6 mils per minute. Okay, we recorded our data. We did that. We refilled. All right, so how does the body increase blood vessel radius? That happens through the action of the smooth muscle that wraps around some of our blood vessels. Some of them have more than others. So if we are increasing the radius, that would be a relaxation of the muscle. Okay, let's see what the next instructions are. So now it's going to have us increase by 0.5 millimeters until we get up to 5. So let's go ahead and go to 2.5. Start. Much faster. Record our data. Got it. And now we're going to refill. So we went up to 30.7 mils per minute. Now we're going to go to a radius of 3. Record the data, refill. Now we're at 63.6 mils per minute, 3.5. Now we've gone up to 117.8 mils per minute. 4. Refill. We'll look at the data in just a minute. We're going to go to 4.5, start, record, okay, refill. Last, we're at 5 millimeters. Record, and let's refill you. So let's take a look at that data. Move the screen up. Well, that's as far as it goes. All right, so from at a radius of 3.5, we're just under 118 mils per minute. But as we increase, look how quickly it's going up. I mean, it's not a linear relationship there. This would produce a curve if we plotted it, but it goes up to 490.6 mils per minute. So let's get caught up on the steps here. Oh, look, we've got a question. Do you think it would be linear? No, it's not going to be linear. And we can actually plot it. Yep, that's what it wants us to do. So here's our plot, right? A linear line would be a direct proportional relationship, but this is a logarithmic relationship where once we get out there, we're seeing bigger increases. How do we get rid of that? Oh, submit. There we go. Okay, that is it on this lab. Let me stop the share. And now I'm going to go to the next exercise, which I've already got set up here. Let me just close things down and switch over. Okay, so this is PhysioEX exercise 5. All of these are in exercise 5. That was activity 1 we just did. And now we're going to do activity 2. Okay, now we're looking at viscosity, the thickness of blood. And there are some elements in this experiment that we really haven't covered in lecture yet. It's covered in the chapter 15 and 16 lecture on blood vessels and blood. So keep in mind that if you're doing this at home, there's certainly some terminology we haven't gotten to, but we will get to. Okay, so we are, make sure I'm on the right thing. This looks like exactly the same experiment. So, okay, so our viscosity is set to 1. Here it is. We're going to hit start. Let's go. Same setup of the experiment. That was really fast. Next, we're going to record our data. There, we got it. So our flow rate was 490.6 mils per minute. Let's refill. What effect do you think increasing the viscosity will have? Well, as it gets thicker, it should slow it down. The fluid flow rate will decrease. Okay, now we're going to increase the viscosity to 2. Here we go. And hit start. Let's see. Record data. So it is slower, quite a bit slower. Let's refill it. And I need to get caught up with the instructions. We did that. We did that. What is the relationship between fluid flow and viscosity? So are they directly proportional, inversely proportional? Well, do we even have enough data to really see that yet? Well, we do. So the fluid flow and viscosity are an inverse relationship. That gets back to that simple equation we looked at in lecture about flow is equal to the change in pressure over resistance, right? Viscosity would be resistance or in the resistance, which would be in the denominator. All right. Let's see what it wants us to do next. Okay, so now we're going to increase the viscosity by 1 all the way up to 8. So we're just going to manipulate those variables. So we're at 2. We're going to go to 3. Start. Okay, record data. Refill. So it is slowing down. We're going to go to 4. Start. Record data. Refill. Well, it's getting slower. We're going to go to 5. We'll look at the data at the end. Record data, refill. We're almost there. Now we're going to go to, whoops, that's the wrong one. 6, start, record data, refill. Is it my imagination or this is getting much redder, huh? to show the thicker blood. Okay, one more. Okay, so let's look at these. So from 4, we're at 122.7 mils per minute. And now it's slowing down, but it's certainly not, the increments are not nearly as wide as we saw up top, right? We went from 490 to 245. That's a pretty big drop. Now we're going from 70 to 61. So it's not a linear relationship here either. Okay, we've done that. Oh, okay. I wanted to look at our data. Let's plot our data. There we go. So it does show that it's a linear relationship. Excuse me, a logarithmic relationship. Oh my gosh, I put my foot in my mouth there. This is a logarithmic relationship. If it were linear, it would be a straight line. Okay. So that is the effect of blood viscosity on flow rate. It slows it down. All right, let me switch to our next one. Get rid of that. We're going to do activity 3 now in exercise 5. Okay, now we're looking at the length of the blood vessel. So another way of thinking about that is how far away are we from the heart? Okay, so our conditions are 100 millimeters of mercury. We're at a viscosity of 3.5 and our radius is 5. Okay, much shorter tube. Okay, let's record the data. Got that, refill it, get our instructions. We did that, we did that. What effect do you think increasing the flow tube length will have? It should slow it down because we're further away. Let's see, let's go ahead and do that. So now we're going to increase the length to 15. We were at 10. So did you see it moved over? It got further apart. We're going to hit start, record data, and now our flow rate decreased, which is what we would expect. We get caught up on our instructions. We did that. We did that. What is the relationship between fluid flow and flow tube length? Are they independent? No. Is their relationship exponential? We didn't even really talk about that option before. And when we're talking about a linear relationship, that is an exponential relationship. But also, the length is something that's going to it's an inverse proportion, inverse relationship. Okay, let me get our instructions. Okay, so now we're going to increase it by 5 millimeters all the way up to 40. Okay, wow, that's a big increase. Okay, so 20, let's start. Record. We'll look at the data after we get done. Now we're going to go to 25. 30. $35. And the last one with a vessel length of 40 millimeters, if I can get there. Okay, so let's take a look. Okay, so our length, here we are. So at 25, our flow rate is 36.3. At 30 millimeters, it's 30.3. At 35, it's 26. And at 40, it is 27.7 mils per minute. Let's plot it. So another logarithmic relationship. Okay, so that is the effect of blood vessel length on flow. We've got one more we're going to do. Let me get over to activity 6. Okay, so now we're looking at stroke volume. And this is a concept we talked about a little bit in chapter 14, but I actually realized after viewing the chapter 14 lecture video when I was correcting it that I didn't explain it enough. So what stroke volume is it's the amount of blood that is expelled in one cardiac cycle. So really, what does that equal? It's relevant to that left ventricle because the left ventricle is what, let me stop the share so you can see me better. The left ventricle is what pumps out to the systemic circulation. So we use the left ventricle to look at stroke volume since that's what's pumped out. But what it is it's the difference between the amount of blood that's present in the ventricle right prior to contraction versus after. So if it's 100% efficient, it would all go out. But there are a number of factors that affect that, which we'll look at some of these variables in this activity. But and those variables and factors can change for us over our lifetime. I mean, cardiovascular disease is a chronic disease that takes a lot of time to build up. So these are some of the things that parameters that can change in a person's lifetime. Their stroke volume become compromised through a number of different factors. So I just wanted to take a minute and explain a little bit better what stroke volume was. All right, let's get back to the last activity that we're going to do for lab 8. So this is activity 6. So we've got 3 different beakers. You notice that they're not all the same diameter. Our left beaker has a pressure of 40 millimeters. We've got a pump pressure of 120, and then our right one is 80 millimeters. We've got a maximum of 10 strokes set, and then the radius between the left and right flow is 3 millimeters. So it says, note that the starting pump, which is the end diastolic volume, is set to 120. So set the volume to 10 by increasing the end pump. So we've got our starting pump is 120 here, and it says to set the volume to 10 millimeters by increasing the end pump volume to 110. Why doesn't it just start there then? So to increase, and this represents the end systolic volume. And these are the 2 factors. So we've got the stroke volume is the difference between the end diastolic volume versus the end systolic. Pre-contraction versus contraction. Systole, pre-systole versus post-systole is the way to think about it. Okay, so we're going to set the stroke volume to 10 millimeters by increasing the ending pump volume to 110. I don't understand why it didn't just start that way. Okay, we did that. Select auto pump. We're going to do that to initiate 10 strokes. It was set on 10 as we began, and we're going to watch the pump. The flow rate is shown in the flow rate display. So that's right over here on the right side. And the pump rate is right below it. So we're going to hit auto pump. Okay, that was interesting. Record data. Let's refill. We'll see, we will see the effect of these as we kind of move and look at the different variables. Why isn't it letting me record? Okay. Is the pump rate analogous to heart rate? What do you think will happen to the rate when you increase stroke volume? It should increase. I mean, that's part of the sympathetic response. That's part of the way to increase our heart rate, if it's low, is to increase the volume of blood going through the body or going through the heart. So let's see. What do you think will happen to the rate when you increase the stroke volume? The pump rate will increase to maintain cardiac output. The pump rate will increase to maintain, it's this one. It's going to input to maintain cardiac output. What we haven't talked about yet, this is in chapter 15, is that the venous side is really a blood pool. So when the body needs more volume to go through to compensate for something like this, it pulls it out of the venous side so that it can maintain the cardiac output. That's a correction to get to homeostasis. Okay, now we get to the experiment. Now we're going to increase the stroke volume to 20 by decreasing the, here we go. We're going to decrease the end systolic volume. Okay, here we go. Sorry, it's just getting to this is not going right. It didn't even let us do the experiment. Let me reset that. Sorry. Okay. We're going to go through this again. Set the stroke volume to 10. Sorry, I've got to repeat this part by increasing the ending pump volume to 110. Okay, so see the stroke volume is 10. And then we're going to hit auto pump. Record data, refill. Did it not like what I did here? Okay, increase the stroke volume to 20 mils by decreasing. So I'm going to, there we go. So I put the end down to 100 and now the stroke volume is 20. So we got there. So but it won't let me do it still. Okay, so stop and think. Why did changing the ending pump volume automatically change the stroke volume? Well, it's because of the relationship between what they are. So our cardiac output is the difference between those two. So if we change the end systolic volume, we're not, right? If we lower that, we're not pumping out as much with the contraction. Okay. I'm just going to guess at this and get through. I want to get to the experiment. I didn't even read what I clicked on there. Sorry about that. Okay, note that the starting pump is set to 120, which it is. Set the stroke volume to 10 by increasing. So the stroke volume is at 70. We're going to increase the end diastolic volume to get it to set the stroke volume to 10. We want the stroke volume to be 10 again. Okay, so here we go. Now the stroke volume's 10. We're going to hit auto pump, see what happens. Record the data. Refill. If the pump rate is analogous to the heart rate, what do you think will happen when you increase the stroke volume? So now we're sending more blood through. It's coming out of the venous side and it's being, it's the stroke volume, which is what's coming out, is increased. So the heart rate needs to increase to do that. So our pump rate will either increase to maintain cardiac output or pump rate will increase to maintain the venous return. Let's go. Why won't it let me go past? There we go. Okay, so now starting pump volume is 120. Set the stroke volume to 10. We just did this. Okay, let's go ahead and do it again. Okay, and we're gonna hit auto pump again. Maybe it's because I didn't record the data. All right, we've got it there now. Let's refill. Oh my gosh. Sorry, guys. I'm just repeating it because I hit the wrong button. Okay, increase the stroke volume to 20. We did this too by decreasing the end. So we're at 20. Okay. Why did changing the end pump volume? We already did this too. Let's do that. There we go. Submit question. Set auto pump to initiate the 10 strokes at a stroke volume of 20. Let's see what happens. Got it. We're going to record the data. Okay, finally, now we've got some data that we can compare. So our rate is quite a bit lower, right? We're got less than about half of the strokes per minute to maintain the same flow. So what's happening, what this is simulating is that there is a compensation that's kicked in, and where that would come from is out of the venous blood supply, because there's a lot of blood in the venous blood supply. Okay, now we're going to look at the effect of incremental increases. So we're going to increase the stroke volume by 10 mils by decreasing the end pump volume and then go through the process. Okay. Auto pump. Record data, refill, and we're going to go to 60. So we'll go through the data at the end again. We've got 2 more measurements. Now, whoops, push the wrong button. 50. It's taking a bit more time, isn't it? Or it seems. Maybe I'm impatient. And 1 more measurement. Oops, wrong button again. Now we're at 60, which is our last measurement. Record data. Okay, so let's see. Oh, I'm sorry. The data table here is not very user-friendly. So as we increased our stroke volume, our rate is dropping, right? We started at 508.7. We're at 254, 169. And then finally, as we get to our higher stroke volumes at 50, it's 101.7 strokes per minute. And then at 60 a stroke volume, it's 84 strokes per minute. So let's go ahead, and the flow has stayed constant because the body is compensating. This is simulating the compensation mechanism that has happened. So let's look at our data too. See, our flow is the same. The pressure is the same. The only thing that's changing is the stroke volume, which is affecting the rate. So the flow has stayed constant with each trial because the cardiac output is equivalent to blood flow. Well, it does estimate, cardiac output does estimate blood flow. Stroke volume is equivalent to blood flow. Well, cardiac output is equal to heart rate times stroke volume. The end diastolic volume isn't changing. Yes, it is. We did change it. The vessel radii aren't changing. Well, they aren't. We didn't look at that. So let's see. There you go. That's the answer. Because cardiac output, that is blood flow, right? Stroke volume is one part of cardiac output. Okay, now we need to look at what happens when we're going to increase the stroke volume by 20 mils. Let's see, by decreasing. That doesn't make sense to me. Increase the stroke volume by 20 mils. Okay, I did that. So now we're at 80 and hit auto pump. So it's pumping it 10 times. That's what this middle thing is. That's the heart. Record data. Refill. How does the heart provide for an increase in stroke volume? It increases by increasing the heart rate. It's by increasing the contractility. The way that we increase this is actually a good question. I'm glad I put the wrong answer. How does the heart compensate for it? The heart doesn't compensate for it by increasing heart rate. That's the effect. That is the sympathetic nervous system that does that. The heart is beating faster in response to that sympathetic stimulation. So it's kind of the way the question's written here. All right. So now we just did this part. Increase the stroke volume by 20 mils by decreasing the pump. We did this. I guess we're going to do it again. So we're going to increase this stroke volume to 100. I went the wrong way. Sorry. Okay. And now we're going to hit auto pump. Notice that it's using much more of the middle cylinder. Pumping it up 10 times. Let's record our data and look at these last 2 points. So let's look from 60 to 80 to 100, which is what you're seeing. Still our flow is the same, but look what's happening to our strokes per minute. They are decreasing because of the increase in stroke volume. Let's plot it. Flow stayed the same, right? But look at the difference in the stroke volume, right? We're not hitting every point, well, we are, it's just how we set it. So, okay. Oh, that's that. I wanted to see if I could manipulate some more of those variables in there, but it's not going to let me do that. Okay, well, that actually does show what we needed to talk about. So I'm going to revisit, I'll apply this lesson more through the chapter 15 lecture, where we look more at the distribution and the pressure dynamics that allow our blood to reach every part of our body. Okay, well, I hope that helped with the understanding of some of these concepts. I'll see you back soon. Take care, everybody. Bye-bye.